We are never still. Even as you listen in the quiet of your room, Earth carries you eastward at nearly 1,000 miles per hour. The entire planet circles the Sun at 70,000 miles per hour. The Sun itself, luminous and vast, orbits the center of the Milky Way at 500,000 miles per hour. And the whole galaxy, with its stars and dust and dark matter, surges through the cosmic microwave background at nearly 800,000 miles per hour. How fast are you really moving? The question seems trivial, the kind a child might ask on a long car ride. Yet it is a question that has no answer. Every instrument we design, every laboratory we build, every thought experiment we conduct, returns the same verdict. Absolute motion cannot be found. Only relative motion, only differences, can be measured. What seems still to you is racing to another. What seems rushing to them is still to you. The paradox of motion is not new. Centuries before Einstein, Galileo sensed that the laws of nature must be the same for observers in steady motion. His shipboard analogy was simple. A ball dropped in the cabin falls straight down. Whether the vessel drifts lazily or speeds across the sea, the sailor sees only the downward drop, unaware of the ship's larger journey. In Galileo's words, the universe is written in the language of mathematics Il Saggiatore, 1623, and that language admitted no absolute speed. A 2019 University Press monograph emphasized that this principle was a radical break from Aristotelian dogma, which had trusted authority more than experiment. Yet Galileo's insight was not the end. For 2 centuries, the Newtonian framework reigned. Time was universal, flowing at the same rate everywhere. Space was the grand stage, unyielding and absolute. Newton himself described time as absolute, true, and mathematical, existing independently of anything external. And within this scheme, the world made sense. Bridges stood, planets obeyed orbits, cannonballs arced predictably, but in the faint glimmer of light itself, something refused to conform. James Clerk Maxwell, in 1861, wove electricity and magnetism into a single tapestry of equations. They declared that light was an electromagnetic wave, and that its speed was fixed, unchanging, and universal. Here the crack began to spread. If Galileo and Newton were correct, the speed of a wave should depend on the motion of its medium. Sound depends on air. Ripples depend on water. Then what was light's medium to answer? 19th century physicists proposed a substance they called luminiferous ether. If ether existed, one could measure Earth's drift through it. Absolute motion would once again be within reach. But experiment after experiment failed. The most famous, by Albert Michelson and Edward Morley in 1887, rotated beams of light at right angles, expecting interference shifts that would betray Earth's motion through ether. None were found. Their precision was 1/40th of what the ether model predicted, yet the result was a void. As Ashby noted in Physics Today 2002, the null result of Michelson-Morley became one of the most consequential negative findings in science. Light had no detectable medium. Its speed appeared the same in all directions, regardless of Earth's motion around the Sun. This was a contradiction Newtonian physics could not mend. If Galileo was right, then no experiment could detect absolute speed. If Maxwell was right, then light always traveled at c, fixed and unaltered. How could both principles be true? The young Albert Einstein, in 1905, faced this rift and dared to claim that space and time themselves must yield. The laws of physics are the same for all observers in uniform motion. He wrote in his paper, "On the electrodynamics of moving bodies, the speed of light in vacuum is constant, regardless of the motion of the source or observer." These postulates demolished ether, toppled Newton's absolutes, and forced the universe to reveal a deeper architecture. Consider the implication. If light's speed is constant, then clocks in motion cannot tick in unison. Rods in motion cannot keep their full length. Mass cannot remain fixed. Our everyday measures of distance, duration, and weight lose their universality. A 2021 National Agency report emphasized how GPS satellites must account for these relativistic effects daily, or the system would fail within minutes. What began as a paradox in a laboratory reshaped how billions navigate the world. Yet beneath these consequences lingers the riddle. If time is relative, then whose time is real? If all motion is relative, then what does it mean to be still? And if light's constancy requires the bending of everything else, what is left that does not bend? Prepare yourselves. We are about to step into Einstein's labyrinth, where light dictates reality itself. If you want to journey deeper into these mysteries, subscribe and stay with us as we unravel the cosmos. Walk with us into this paradox, and together we will uncover why time refuses to be absolute. And to do so, we must return to Galileo, whose experiments on ships and inclined planes planted the seed of relativity long before Einstein gave it its name. The great turning of science did not begin with Einstein. Long before the 20th century shook the pillars of certainty, a lone Florentine gazed at falling bodies and asked whether nature obeyed rules unseen. Galileo Galilei, born in 1564, challenged the weight of authority that had chained inquiry for nearly 2,000 years. Aristotle had said that heavier objects fall faster than lighter ones. The Greeks argued, reasoned, and asserted, but rarely tested. Galileo instead rolled spheres down inclined planes, timed their descent with his pulse, and discovered that all objects fall alike. In this simple act, he fractured the dominion of pure logic and replaced it with experiment. What Galileo uncovered was more than a correction to Aristotle's mistake. He uncovered a principle that would become the seed of relativity itself. If the laws of physics are valid at all, he reasoned, they must be valid everywhere and for everyone in uniform motion. This conviction later came to be known as the principle of relativity. A ball dropped in the cabin of a moving ship falls straight to the floor as if the vessel were still. The sailor perceives only the vertical plunge. An observer on shore, however, sees a diagonal arc, the ball carrying forward with the ship even as it falls. Both perspectives are valid. Both are consistent with nature, and yet no one inside the ship can tell, by any experiment, whether they drift gently or surge across the sea, centuries later. This same analogy would be lifted into the skies. Imagine spilling a cup of coffee on an airplane flying 600 miles per hour. To you, the liquid falls straight down into your lap. To someone watching from the ground, the coffee is not simply falling, it is also racing forward with the plane at 600 miles per hour. This invisible momentum persists because motion is relative, not absolute. A 2007 University Press study on the history of science noted that Galileo's insight, disguised in ordinary examples, marked one of the most radical shifts in human thought. The heart of the principle is simple. Absolute velocity does not exist. Only velocity relative to another body can be meaningful. Galileo knew this before precision clocks, before spectroscopy, before the elaborate instruments that would come centuries later. He knew it from careful observation. He saw that what matters are changes in velocity, not the elusive notion of motion itself. Newton would inherit this view and extend it into his laws of motion. Yet Newton's framework kept time and space as absolutes. Galileo's shipboard experiments showed that within an inertial frame, the laws of nature remain constant. Newton systematized this, saying that an object at rest remains at rest, and an object in motion remains in motion unless acted upon by a force. But the true significance lies deeper. You cannot detect constant motion from within. You cannot build an experiment that reveals whether your ship, your plane, or even your planet glides through some cosmic stillness. The universe offers no privileged reference frame. This realization was unsettling. If the Earth spins on its axis at nearly 1,000 miles per hour, orbits the Sun at 70,000, and drifts with the solar system at 500,000, then what does it mean to be still? Galileo's principle suggested that stillness is an illusion, a local convention. What feels solid beneath our feet is in truth swept along an invisible current. A 2016 peer-reviewed analysis described this as one of the most humbling discoveries in early modern physics. It taught us that perception of rest is no more than a convenient story. Galileo's experiments were not just demonstrations for curious minds, they were manifestos against the tyranny of untested belief. By insisting that falling bodies, pendulums, and inclined planes be measured, he proclaimed that science must rest on evidence. His principle of relativity was, in its time, a declaration of intellectual independence. The cosmos, he revealed, does not play favorites. The implications extend far beyond Renaissance Italy, for if no motion is absolute, then only relationships bind us to the world. Every velocity is tied to something else. Every rest is provisional. This lesson would echo into Einstein's century, where light itself refused to conform to the old laws. But to appreciate the enormity of Einstein's leap, we must first see how Newton took Galileo's seed and built a universe of celestial mechanics upon it. And so, from Galileo's ship and pendulums, we move to Newton's inheritance, where motion was made precise and the stage set for the first cracks to appear. When Isaac Newton published his Principia in 1687, he codified the framework that would govern human understanding of motion for more than 2 centuries. The laws of motion and universal gravitation provided a clockwork vision of the cosmos, where planets wheeled in predictable orbits and falling bodies obeyed a universal rule. Time was absolute, flowing steadily like a river that could neither quicken nor slow. Space was an infinite stage, rigid and unmoving, on which every event unfolded. This Newtonian inheritance was the air scientists breathed, the foundation on which architecture, navigation, and astronomy rested. In this universe, velocity was relative, but time was not. Observers might disagree on how fast an object moved, but they would agree on how long it took. A second in London was a second in Beijing, a second in the farthest reaches of the solar system. Newton himself described this with striking clarity, calling time absolute, true, and mathematical in his Principia. And for centuries, the world seemed to comply. The calculations predicted eclipses, guided explorers across oceans, and revealed the subtle dance of comets. Yet into this serene architecture entered electricity and magnetism. What had been curiosities in the 17th century became, by the 19th, forces of deep significance. Static charges, sparks, and magnets hinted at hidden unity. It was James Clerk Maxwell who, in the 1860s, unveiled the equations that fused these phenomena into one. They were more than a set of laws. They were a revelation, describing a universe where electric and magnetic fields were woven together and where light itself emerged as their offspring. Maxwell's equations declared that electromagnetic waves propagate at a definite speed, a constant derived from the properties of space itself. When he calculated that number, it matched the measured speed of light. This was more than coincidence. Light, he realized, was an electromagnetic wave. The glow of the sun, the shimmer of a candle, even the invisible pulse of radio, all were manifestations of fields vibrating through the void. As a 2017 University Press monograph put it, Maxwell had written light into the very fabric of physics. But here the first crack in Newton's marble appeared. For if light is a wave, what medium carries it? Sound requires air. Ripples require water. No known wave travels without a medium. Scientists gave this hypothetical substance a name, the luminiferous ether. It was imagined as filling all of space, invisible, yet essential, a subtle sea through which light moved. If ether was real, then one could measure Earth's velocity through it, at last distinguishing true motion from relative. The ether was not only plausible, it was expected. Surely the cosmos must be filled with something to sustain light across the void between stars. Yet the existence of this medium clashed with Galileo's principle that no absolute velocity can be measured. If the ether existed, then there must be a preferred frame. the one in which ether rests, that frame would be absolute, and the long-held principle of relativity would be undone. Scientists of the 19th century wrestled with this tension. On one hand, Newton's laws had proven infallible in their domain. On the other, Maxwell's equations insisted on a constant speed of light that seemed to ignore the motion of the source or the observer. The universe was whispering two contradictory truths. Which should be trusted? A 2015 peer-reviewed analysis argued that this contradiction was not a minor technicality, but a fundamental fracture in classical mechanics. Consider the analogy of a river. Throw a stone into a pond, and ripples spread equally in all directions. Throw a stone into a river, and the current carries the ripples faster downstream and slower upstream. If ether existed, Earth moving through it should reveal itself in precisely such variations. Light traveling downstream should move faster than light traveling upstream. The absence of such variation would imply something extraordinary. Either ether does not exist, or our understanding of motion itself is flawed. The Newtonian world, once solid and seamless, now carried hairline fractures. These cracks widened each year as experiments grew more precise. The confidence of centuries began to waver. And in the laboratory of Michelson and Morley, the fracture would open into a chasm, hole. By the late 19th century, physicists were certain that if light was a wave, then it must ride on a medium. They named this invisible sea the luminiferous ether. It was imagined as an all-pervading substance that filled every corner of the universe, subtle enough to avoid detection, yet sturdy enough to carry vibrations at the immense speed of light. The ether was taken for granted. Just as air is taken for granted when we hear a sound, the expectation was clear. Earth moves through the ether, just as a swimmer feels the current of a river. Our planet, spinning and orbiting, should be pushing against this unseen ocean. That meant the speed of light could not be the same in every direction. Moving with the ether current should make light faster. Moving against it should slow it down. The analogy was irresistible. As a 2009 academic history of physics observed, most physicists regarded ether as indispensable. To deny it was to risk leaving light unsupported in the void. If this were true, detecting the ether ought to be straightforward. Measure the speed of light along different directions. Note the difference. Calculate Earth's velocity through the medium. Yet as the 19th century reached its end, no such experiment yielded a consistent result. It was into this puzzle that Albert Michelson and Edward Morley entered in 1887. Michelson, a master of optics, had already devised an instrument of remarkable precision, the interferometer. This device split a beam of light into two paths set at right angles, reflected them back with mirrors, then recombined them. If the beams traveled at slightly different speeds, the recombined light would produce shifting patterns of bright and dark. These interference fringes were exquisitely sensitive, capable of detecting differences as small as a fraction of a wavelength. The interferometer became the gold standard of precision measurement. Placed on a floating marble slab supported by mercury to reduce vibration, it could be rotated slowly to test every orientation. Michelson and Morley reasoned that if Earth was moving through ether, then as the apparatus turned, the interference fringes would drift back and forth in rhythm with the invisible current. The predicted shift was not trivial. It was large enough to be unmistakable. And yet, nothing. No matter how the instrument was rotated, no matter what time of day or season of year, the speed of light appeared the same in every direction. The expected shift never came. Their null result was devastating to the ether hypothesis. As Ashby explained in Physics Today 2002, the Michelson-Morley experiment revealed a contradiction at the heart of physics. The presumed medium for light did not behave as required, or perhaps did not exist at all. The implications were profound. If ether was real, Earth must somehow drag it perfectly, shielding us from detection. If ether was not real, then light was unlike any other wave ever known. Michelson himself struggled with the outcome. Even after winning the Nobel Prize in 1907, he remained convinced that ether must exist, hoping some flaw in the apparatus had hidden it. But repeated experiments by others, each more precise, confirmed the same result. A 2018 peer-reviewed review noted that modern tests show no directional change in light speed down to 1 part in 10^18, a level of certainty unimaginable in the 19th century. The failure to detect ether was not simply a technical oddity. It undermined the very foundation of absolute space and time. If the speed of light was independent of Earth's motion, then the Newtonian framework was in jeopardy. What could preserve both Galileo's principle of relativity and Maxwell's equations? The answer would come not from further instruments, but from a young clerk in a patent office who dared to imagine that space and time themselves must bend to accommodate light. The ether had been the last scaffold holding up the Newtonian edifice. With the Michelson-Morley null result, that scaffold cracked. And into the void stepped Einstein, carrying two postulates that would redefine reality. When Albert Einstein turned his attention to the puzzle of light, he was not a professor with a grand laboratory. He was a patent clerk in Bern, reading scientific journals during his breaks, thinking in solitude. Yet from that unlikely post came one of the most revolutionary papers in the history of science. In 1905, in Annalen der Physik, he published on the electrodynamics of moving bodies. The paper was short, without illustrations or references. Yet it overturned the scaffolding of Newtonian space and time. Einstein began with two deceptively simple postulates. First, the laws of physics are the same for all observers moving at constant velocity. This was Galileo's principle written anew, elevated from ships and coffee cups to the entire universe. Second, the speed of light in a vacuum is constant, the same for every observer regardless of motion. These two postulates could not be reconciled with Newton's absolutes. To keep them both, one had to sacrifice the idea of universal time and fixed space. The consequences cascaded outward. If the speed of light never changes, then the way we add velocities must change. In everyday life, velocities add linearly. A swimmer moving at 2 miles per hour downstream in a river flowing at 5 adds up to 7, but with light, this arithmetic fails. Imagine a spacecraft moving at half the speed of light firing a laser forward. Common sense would suggest the beam races ahead at 1.5 times the speed of light. Yet Einstein insisted it must still move at exactly c. To resolve the paradox, he gave us a new formula for adding velocities u plus v or 1 plus u of c2. This formula looks abstract, but its meaning is profound. For small velocities compared to c, it reduces to simple addition. But as speeds approach light, the denominator bends the result back towards c. No matter how fast you go, adding light to your motion never breaks the barrier. A 2014 peer-reviewed physics review noted that this velocity law has been tested in particle accelerators to extraordinary precision. Every high-energy experiment confirms what Einstein declared from the patent office. The new arithmetic of speed was only the beginning. Einstein also introduced a scaling factor, a measure of how lengths, times, and masses change as velocity increases. He called it GOL, the gamma factor, defined by Jachigiso E1, V2 to C2. At ordinary speeds, V is tiny compared to C, so G is nearly 1, but as V nears the speed of light, the denominator shrinks, and J grows without limit. At 0.9 C, G is about 2.3. At 0.99 C, it climbs to 7. At 0.99 C, it soars to thousands. This factor reshapes reality. Lengths in the direction of motion shrink. Mass appears to increase. Time itself dilates. The faster you move, the more the universe distorts around you. As Einstein wrote in 1905, time and space are modes by which we think, not conditions in which we live. A 2019 University Press monograph argued that judge is not merely a correction, but a doorway into the structure of space-time itself. The most haunting implication lies at the limit. If Joju tends to infinity as v approaches c, then the energy required to accelerate a mass to light speed becomes infinite. No rocket, no star, no force of nature could push matter across that boundary. Light is unique, a realm for photons alone. To travel faster would require infinite energy, and infinite energy would collapse into a black hole. The speed of light is not just a number, it is a horizon. It is the edge of the possible. Here lies the boundary of existence. We live in a universe where c is absolute. It shapes what journeys can be made, what stars can be reached, what futures can unfold. In particle accelerators, protons accelerated to 0.9999999 c acquire gauge factors of tens of thousands, behaving with masses magnified far beyond rest. As a 2020 National Laboratory report noted, these experiments confirm Einstein's vision with exquisite fidelity. Nature bends to the postulates, never to our intuition. And so we leave Newton's marble behind and step into a flexible cosmos. Velocities no longer add as they once did. Time no longer ticks as it once seemed. Space no longer stretches in quiet absolutes. With Einstein's postulates, the very stage of reality becomes pliable, molded by motion and constrained by the light that illuminates it. But if the rules of velocity and gauge reshape our equations, what do they do to our experience of time? The answer emerges in a simple thought experiment, where a beam of light bounces between two mirrors and shows that clocks themselves cannot agree. Einstein loved thought experiments. They were his workshop, his way of stripping away distraction until only the principle remained. He once said that the purpose of such an exercise was to make it as simple as possible, but not too simple. Among his most famous devices is the photon clock. Imagine two perfect mirrors, one above the other, and a single photon bouncing endlessly between them. Each reflection marks a tick of the clock. The setup is pristine, free from gears or springs, relying only on the constancy of light. Now picture this clock at rest beside you. The photon bounces vertically, up and down, at the speed of light. Every tick is identical. The rhythm is steady. This is our measure of time. But place the same clock inside a spacecraft rushing past at 90% of light speed. To the crew, nothing changes. The photon still goes up and down. The ticks are as steady as before. To us, watching from the outside, the story is different. The spacecraft is moving, so the photon must trace a diagonal path, zigzagging as the mirrors race forward. Each tick takes longer, because the photon's journey is longer. Yet it can never exceed the speed of light. The result is inescapable moving clocks run slow. This slowing of time is not an illusion. It is measurable, predictable, and universal. At 90% of light speed, the gamma factor is about 2.3, meaning that while 100 ticks pass in our clock, only 43 pass in the moving one. If we push closer to light speed, the difference grows extreme. At 0.99 c, the gamma factor is 7. At 0.999 c, it is 22. Every process within that moving frame slows by the same factor heartbeat. Thought, chemical reaction, even decay of particles. As a 2019 peer-reviewed physics experiment confirmed, time dilation applies equally to every known clock. The symmetry of relativity deepens the mystery. To the crew inside the ship, their clock is normal. It is we on Earth whose clocks appear to be slow. Both perspectives are correct, because there is no absolute time. Einstein demolished Newton's absolute, true, and mathematical time, replacing it with a web of local times, each valid within its own frame. As a University Press monograph from 2015 argued, this was not just a change of numbers, but a collapse of universality itself. One might be tempted to ask which clock is truly right. The unsettling answer is both. There is no cosmic master clock ticking behind the scenes. Time is what each observer measures, and what each measures depends on motion. This relativity of time, strange as it sounds, is confirmed by experiment after experiment. Muons created by cosmic rays. Particles that live only a millionth of a second at rest survive long enough to reach Earth's surface because they are moving near light speed. Their clocks are slow, and so their lives are extended. Without this dilation, almost no muons would reach us. As a 2021 National Laboratory report noted, particle detectors on Earth confirm this every day. Thought experiments help us grasp the principle, but reality drives it home. Every airplane, every satellite, every particle beam reveals it. Global Positioning System satellites orbit Earth at thousands of miles per hour. Their onboard clocks run slightly slower than those on the ground due to special relativity, while general relativity pushes them slightly faster due to weaker gravity. Engineers must apply corrections on the order of billionths of a second. Without them, GPS navigation would be useless within minutes. Our cars find their way. Our phones locate us. Because we live in a world where Einstein's photon clocks rule. Time dilation is not merely an abstract twist of equations. It is a reshaping of reality. It says that what you call a second and what another calls a second may never agree if you are in motion relative to one another. It says that simultaneity itself dissolves, that two observers cannot agree on what now means if they are moving differently. In the words attributed to Einstein in a 1926 lecture, time is what a clock measures. Nothing more, nothing less. And yet, how unsettling it is to realize that every clock measures differently. We may ask if all time is relative. Is there any truth beyond perspective? The photon clock whispers no. Each frame has its own rhythm, its own unfolding of events, equally real, equally valid. And this strangeness, far from remaining theoretical, reaches into the biology of life and the devices of civilization. To see how, we must turn to the rain of cosmic particles that bathe our atmosphere and to the satellites that orbit above us. High above us, beyond the shielding of the atmosphere, the cosmos hurls particles toward Earth at near light speeds. These are cosmic rays, fragments of nuclei born in violent astrophysical events, exploding stars, and perhaps even more exotic accelerators scattered across the universe. They strike the upper atmosphere and trigger cascades of collisions, producing showers of secondary particles. Among these are muons, cousins of the electron, unstable and short-lived. At rest, a muon survives for only about 2 millionths of a second. In that span, even if moving at light speed, it should cover less than half a kilometer before vanishing. The Earth's surface, many kilometers below, should be out of reach. And yet muons do arrive. In fact, they account for the overwhelming majority of the charged particles that reach the ground. The reason is time dilation. From our perspective on Earth, the muons are moving at such extreme velocities that their internal clocks are slowed by factors of 10 or more. Instead of living for 2 millionths of a second, they live long enough to traverse tens of kilometers of atmosphere. Detectors on mountaintops, in laboratories, and even in high school classrooms have measured this rain of muons. Their very arrival is a testament to relativity. As a 2016 peer-reviewed particle physics study showed, the observed number of muons at sea level matches perfectly with predictions from time dilation. Without this effect, the surface of Earth would be almost free of muons, and life's evolutionary history might have looked very different. This claim is not mere speculation. Radiation from cosmic rays, including muons, contributes significantly to our genetic mutations. Most mutations are harmful or neutral, but a small fraction prove advantageous, and through them evolution marches forward. A 2018 University Press monograph noted that without a steady flux of radiation-driven mutations, the pace of evolution would have been far slower. In this light, relativity may have shaped the trajectory of life itself. If time did not dilate for muons, many mutations would never have occurred, and the genetic possibilities that eventually led to humans may have been delayed or denied. The consequences of relativistic time are not confined to cosmic origins. They operate daily in the infrastructure of our civilization. Consider the constellation of satellites orbiting Earth at an altitude of more than 20,000 kilometers, the Global Positioning System. Each satellite carries atomic clocks that broadcast timing signals. Receivers on Earth calculate their position by comparing these signals. The accuracy must be exquisite, down to billionths of a second, but satellites move quickly, about 9,000 miles per hour, and they orbit in weaker gravity. Both special relativity and general relativity shift the rates of their clocks. Special relativity slows them. General relativity speeds them. The net effect is about 38 microseconds per day faster than clocks on Earth. It sounds negligible, but without correction, GPS positions would drift by kilometers within a single day. Engineers build relativity into the system itself. The satellites are calibrated so their clocks run at the correct rate from our perspective on Earth. As Ashby explained in Physics Today, 2002, without relativistic adjustments, GPS would be worthless. Every time a driver follows the blue line on a screen. Every time a rescue team finds a lost hiker. Every time a plane lands safely on a runway. Relativity is at work. The photon clock experiment is not confined to imagination. It lives in orbit above us, guiding modern civilization. What began as a paradox in a laboratory has become a necessity of daily life. The universe enforces its laws whether we acknowledge them or not. We do not perceive time dilation directly in our bodies, yet our technologies demand its inclusion. We do not feel cosmic rays striking us, yet our DNA bears their imprint. Relativity, in this sense, is not distant theory but immediate condition. It writes itself into our genes and into our machines. And still, beneath all the equations and consequences, the deeper question endures. If time can stretch and contract depending on motion, then there is no single cosmic now. Each observer inhabits a different rhythm of duration, each life unfolding on its own clock. When satellites and particles and human minds all tick at different rates, what does it mean to speak of reality as one? To approach that question, we must leave physics and enter philosophy. We must confront the possibility that truth itself is bound to perspective, and that time, our most familiar companion, may be nothing more than a local story. We arrive now at the quietest, yet most unsettling, chamber of the journey. The equations have been tested, the experiments confirmed, the satellites corrected, the muons observed. No contradiction remains in the physical record. Yet when we gather the fragments into one vision, what they reveal is not simply physics. They reveal a profound shift in how existence itself must be understood. Time, once thought absolute, has fractured into local rhythms. Each observer carries a private clock, unshakable in its own truth but irreconcilable with others. Einstein wrote in 1926 that time is what a clock measures. He meant it literally. Yet the phrase carries an echo of metaphysics. If clocks disagree, then so does time itself. There is no universal beat, no cosmic metronome that governs all things. The universe is not a grand hall where every instrument follows the same conductor. It is an orchestra in which each musician follows a score that shifts with motion. This collapse of universality unsettles more than equations. It unsettles our sense of identity. We imagine a shared now, a present we inhabit together. Yet relativity says otherwise. Two observers moving differently will not agree on what events are simultaneous. One may declare that a star flared in the sky as a bell tolled on Earth. Another may deny the coincidence. Both are correct. The notion of simultaneity itself dissolves. As a 2017 University Press monograph argued, relativity forces us to see that now is a local story, stitched by motion and perspective. The implications ripple outward. If there is no shared present, then the very idea of history bends. Past and future are not fixed tapes that spool identically for all. They are webs of causality, woven differently in each frame. The cosmic order becomes a library where each page tells the story from a vantage, and no vantage is final. We are left with narratives rather than absolutes. Consider again the muons born high in the atmosphere. To us, their lives are stretched by time dilation. To themselves, no stretching occurs. Both accounts are real. Our evolutionary path, seeded by their penetration into our genes, owes itself to this dissonance. Without the relativity of time, humanity might not exist. As a 2021 peer-reviewed study of cosmic radiation exposure emphasized, life on Earth is inseparably tied to relativistic phenomena. Our very bodies bear the signature of time's plasticity. And consider the satellites above us. Every direction we take from a GPS screen is proof that time cannot be trusted to tick the same everywhere. The circuitry of civilization requires us to live in Einstein's world. We navigate, we communicate, we land planes, all because time has become elastic. As Ashby noted in Physics Today 2002, the practical success of relativity is so total that we forget its strangeness. We forget that every instruction whispered from orbit is a reminder that no single truth of time exists. Here, the philosophical echo grows loud. If reality is shaped by perspective, then truth itself may not be singular. This is not to say truth vanishes, but that it is plural, woven from frames of reference. What you call rest, another calls motion. What you call a second, another calls two. What you call now, another calls then. The cosmos allows no referee to decide. And yet, amid this plurality, there is one invariant: light. Its speed is constant for all. The line that unites every frame, in a universe where everything else bends. Light is the horizon of truth. It is the message in the bottle, tossed across space-time, received differently by each observer yet carried at the same pace. That constancy is the thread that stitches the relativistic fabric together. Without it, no coherence would remain. The echo, then, is double. On one side, relativity strips us of absolutes, leaving us with perspectives, private clocks, fractured simultaneity. On the other, it gifts us with the unyielding constancy of light, the one truth all observers must share. We live balanced between these poles, caught between plural time and singular light. What does this mean for us? It means that reality is not the rigid stage Newton described. It is a weaving, a shifting interplay of vantage points. We are beings moving through a cosmos that will not grant us stillness. We are stories told by the rhythm of our own clocks. Aware that others tick differently, it means that truth is deeper than consensus, broader than perception, and stranger than intuition. And so we close not with answers, but with a question. If time itself bends for every observer, is there any truth beyond perspective? The echo of relativity invites us to search.